Good evening, ma'am.
Good evening, sir.
Yes, ma'am. Make me host, ma'am.
Good evening, sir.
Yes.
Can start now, sir.
Yes, ma'am. Yes, ma'am. We did oxygen yesterday, right? And we didn't do sulfuric acid. We will do sulfur. Ozone also we finished yesterday, right? Now compounds of sulfur we need to learn. All right, we will learn about sulfur. So I will not use the PPT. For chemical reactions, I will teach you, but otherwise for the preparation part of it, all that I will use this only. Next is sulfur. Sulfur is also a 16th group element, and sulfur exists as S8. Sulfur, 1 minute, what happened? Sulfur exists as S8. Sulfur exhibits allotropic forms, rhombic, yellow rhombic sulfur, and monoclinic sulfur. This is also called as beta sulfur. Sulfur, as I told you, it exists as S8. It has a twisted structure, or it has a structure called as puckered structure, Puckered, puckered structure. So puckered structure will be in the form of a crown like this. It will be in the form of a crown like this. So this structure is called as a puckered structure, or is also called as a twisted structure. Sulfur exists as S8. Now, compounds of sulfur will have to learn, or how do we convert alpha sulfur to beta sulfur? So rhombic sulfur to monoclinic sulfur otherwise. This monoclinic sulfur is also called as beta sulfur. So rhombic sulfur is also called as alpha sulfur. When this rhombic sulfur is heated to 369 Kelvin, above 369 Kelvin, we get beta sulfur. And this beta sulfur, below 369 Kelvin, it will get converted to alpha sulfur. It's a reversible process. So this is the introduction with the topic sulfur. We need to learn the compounds of sulfur. The first compound of sulfur, what we are supposed to learn is sulfur dioxide. Sulfur dioxide. The sulfur dioxide is represented as SO2, sulfur dioxide. How can we prepare sulfur dioxide? The laboratory method, or maybe not the laboratory method. In general, sulfur is prepared by heating or burning sulfur, in more specific, burning sulfur in air. When we burn sulfur in air or oxygen, sulfur gets oxidized to sulfur dioxide. Sulfur is a solid. Sulfur is a solid. This gets oxidized to sulfur dioxide. So when we burn sulfur in the presence of oxygen or air, sulfur gets converted to sulfur dioxide. The second is laboratory method. Laboratory method. In the laboratory, we can prepare sulfur dioxide by various reactions, but the amount of sulfur dioxide prepared in the laboratory will be less. So sulfur dioxide is prepared in the laboratory by treating sulfite salts or hydrogen sulfides, bisulfides, hydrogen sulfides with acids, with hydrochloric acid or with sulfuric acid. So any sulfite salt or a bisulfite salt if you treat it with hydrochloric acid or sulfuric acid dilute, sulfur dioxide gas will be liberated. So sulfite is also present in the first group in the acid radical analysis. In your laboratory or in PUC, we have only carbonate radical. We don't talk about sulfite radical. But remember, sulfite radical also is present in the first group. Now, sulfite is SO3. Sulfate is SO4. Sulfite is SO3, sodium sulfite. Aqueous solution of sodium sulfite, if you treat dilute hydrochloric acid, what happens is these two Na and these two Cl gets eliminated as NaCl as a product, 2 moles of NaCl, aqueous. Plus, now you can see sulfur trioxide, 3 oxygen you have. In this 3 oxygen, 1 oxygen reacts with water to form, reacts 2 hydrogen to form water, and the gas liberated is sulfur dioxide. So sulfite salts, when you treat it with dilute acids like HCl or sulfuric acid, we get sulfur dioxide. Now, if you take bisulfite, if you take sodium bisulfite, NaHSO3, when this NaHSO3 is treated with dilute acid, this Cl and this Na gets eliminated as NaCl, aqueous. It will be in the solution state, aqueous. This hydrogen, one of the oxygen gets eliminated as water, one of the oxygen from here. So left out will be sulfur dioxide. So sulfur dioxide can be prepared in the laboratory by treating sulfite salts or bisulfite salts with a dilute acid. Now, how do you prepare sulfur dioxide in large scale? Large scale, sulfur dioxide is prepared by roasting iron pyrites. Roasting iron pyrites. Now, iron pyrites is FeS2. Roasting, it's a sulfide ore. When we roast it in the presence of oxygen, roasting is always in the presence of oxygen. Heating or burning in the presence of oxygen will be called as roasting. So when we burn it in the presence of oxygen, heat it in the presence of oxygen, we get sulfur dioxide gas plus 2 moles of ferric oxide. So sulfur dioxide in large is prepared by roasting sulfide ore, iron pyrites. When we roast iron pyrites, the sulfur dioxide gas is prepared in large quantity. Now, this is the preparation of sulfur dioxide. Now, we have to learn with the properties of sulfur dioxide. We will learn the properties of sulfur dioxide here. See, the preparation I've given you, sulfur on burning with oxygen, you get sulfur dioxide. Sulfite salts treated with acid, you get sulfur dioxide. In large quantity, it is prepared by roasting iron pyrites, that is iron sulfide. Now, sulfur dioxide is a colorless gas. It's a colorless gas, but it has a very pungent smell, it's a pungent smelling gas. It is highly soluble in water. It liquefies at room temperature at 2 atmosphere, and its boiling point is 263. Did you follow this so far?
Yes, sir.
Yeah. Now we learn the chemical properties. Now, the most important chemical property is bleaching action. I will teach you this bleaching action in a few minutes' time. But first property is, how do we know that sulfur dioxide is acidic in nature? Acidic nature we have to first learn. Now, we know that water is neutral, mostly. It's an amphoteric in nature, but we consider it to be neutral because pH is 7, neutral. There is sulfurous acid. It is acid. Sulfur dioxide gas, when you pass into water, you get sulfurous acid. So formation of acid indicates the nature of sulfur dioxide to be acidic. All right, because water is neutral and the product is acidic, it means the nature of sulfur dioxide also should be acidic. The second reaction which proves that sulfur dioxide is acidic is sulfur dioxide gas when you pass into sodium hydroxide solution, aqueous sodium hydroxide solution. When sulfur dioxide gas is passed into aqueous sodium hydroxide solution, we get aqueous sodium sulfate. This aqueous sodium sulfite, sodium sulfite. The sodium sulfite is a salt. So acid and a base will react. Sodium hydroxide, we know it's a very well-known base. That means the nature of sulfur dioxide should be what? Acidic. So acid and the base reacts to form salt. So these two reactions clearly gives us the information that sulfur dioxide is acidic in nature. Now, addition reaction. This is also one more reaction which gives sulfur dioxide to be acidic. That's fine. Next is addition reaction. Now, when we say addition reaction, when sulfur dioxide is made to react with chlorine, sulfur dioxide undergoes addition reaction with chlorine in the presence of charcoal as a catalyst to form sulfuryl chloride. So here the catalyst is charcoal. So sulfur dioxide, when allowed to react with chlorine, we get sulfuryl chloride. Sulfuryl chloride. Sulfuryl chloride. The sulfuryl chloride acts is due to the formation of addition product. It's an addition product. So sulfur dioxide reacts with chlorine to form sulfuryl chloride. Next reaction, this is called as addition reaction. The first one, we proved that sulfur dioxide to be acidic in nature. The second reaction is addition reaction. The third reaction is also an addition reaction, or it also can be called as oxidation reaction. So sulfur dioxide is a gas. When we oxidize sulfur dioxide using vanadium pentoxide as a catalyst, we get sulfur trioxide. Since oxygen is added, we call it as addition reaction, but it is actually oxidation. Here, the oxidation number of sulfur is +4. Here, the oxidation number of sulfur is +6. Increase in oxidation number will be called as oxidation. So 3 types of chemical properties we learned. The first one is addition nature. Second one is first one is acidic nature. The second one is addition reaction. The third one is oxidation reaction. Now, we have to learn the bleaching action of sulfur dioxide. Bleaching, what is bleaching? Bleaching means removal of color. Now, this bleaching action of sulfur dioxide also can be called as a reducing action. Why it is also called as a reducing action is because this is important question. Bleaching action is a very important question. Now, why this is called as reducing agent is because when sulfur dioxide gas is passed into water, sulfuric acid, H2SO4 is formed, giving you nascent hydrogen. Anything which gives nascent hydrogen will be called as a reducing agent. Will be called as reducing agent. Anything which gives nascent oxygen will be called as oxidizing agent. Here, now sulfur dioxide in water or in moisture, sulfur dioxide acts as a good reducing agent in the presence of moisture. Moisture is nothing but water content. Sulfur dioxide reacts with water to form sulfuric acid, giving you nascent hydrogen. This nascent hydrogen being reactive, it will react with the colored matter. Colored matter in any clothes, if you get any clothes stained, to remove the color, we can remove the color by treating it with sulfur dioxide also, because sulfur dioxide will release H+ ions, nascent hydrogen. These nascent hydrogens are reducing in nature. It will react with the colored matter and color will be removed and the cloth or any other material becomes colorless. So this property is called as bleaching action, or it is also called as reducing property. I hope you follow this bleaching action. So this bleaching action is because of the reducing nature, because it gives what? Nascent hydrogen. It is not because of oxidation. Please remember, it is because of reducing action, nascent hydrogen. Now, what's the structure of sulfur dioxide? The structure of sulfur dioxide is angular. Structure of sulfur dioxide is angular structure. Now, when we say angular structure, sulfur dioxide is double bond O, single bond O. You have a pair of electron on sulfur. You have 2 pairs of electron here, and we have 3 pairs of electron here, and lone pair of electron. This will be stabilized by a resonance. We can write like this. Can be represented as a resonance structure. This is the structure of sulfur dioxide. Now, what are the uses of sulfur dioxide? Now, uses, if they ask you, one is used in the manufacturing of sulfuric acid, H2SO4. We can use it as a bleaching agent. This is important. They can ask you, what is an anti-chlor? What is used as an anti-chlor? Anti-chlor. So ANTICLOR. Anti-chlor is nothing but removal of chlorine, excess chlorine from bleached fabrics. So anti-chlor, sulfur dioxide removes excess chlorine from bleached fabrics. From the bleached fabric, if you have excess chlorine, that excess chlorine can be removed by sulfur dioxide, and that property is called as anti-chlor. Remember this anti-chlor, because we don't know from where the objective questions can be asked. 1 mark questions can be asked. So here, some of the reducing natures they've given. So sulfur dioxide reduces ferric ions to ferrous ions. So when ferric ions, ferric chloride, ferric sulfate is treated with sulfur dioxide, aqueous sulfur dioxide, so we get ferrous ions. Likewise, sulfur dioxide will reduce manganese. Manganese has +7 here. Here, manganese has +2. So this is sulfur dioxide behaves like a reducing agent. I've given you the structure, resonance structure of sulfur dioxide also. Now, questions, we will learn it later as we were discussing previously. We will learn one 3-mark question in detail. That is, the next compound is sulfuric acid. The next compound is sulfuric acid. The sulfuric acid, the molecular formula, please pay attention. We have learned the preparation of ammonia by Haber's process. We have learned preparation of nitric acid by Oswald's process. We have to learn the preparation of sulfur dioxide by contact process. So in this 3, 1 question is compulsory for 3 marks. Compulsory for 3 marks. So it's easy to score 3 marks from this chapter. Even though it's a lengthy chapter, it's easy to score 3 marks, because I hope that ammonia and nitric acid synthesis we have learned. And we will learn today the preparation of sulfuric acid. Sulfuric acid is H2SO4. The sulfuric acid is called as king of chemicals. Sulfuric acid is called as king of chemicals. Second one, the sulfuric acid is also called as oil of vitriol. Oil of vitriol. Sulfuric acid is a liquid. It looks like a liquid. You have seen in the laboratory used concentrated sulfuric acid. It's in the form of an oil. If you would have observed very keenly, you will know that it is not in the form of water. It does not freely flow. It's in the form of an oil. It has a definite geometry. The shape of sulfuric acid is tetrahedral. Since it has a tetrahedral, any liquid will not have any geometry. Any liquid, for that matter, will not have any particular shape. But sulfuric acid has a particular shape, tetrahedral shape. Therefore, it is called as oil of vitriol. The sulfuric acid is a good oxidizing agent. It's a good oxidizing agent. All right. And the sulfuric acid is also a good dehydrating agent. Removal of water is called as dehydration. So sulfuric acid can be used to remove water. Therefore, it is also called as a dehydrating agent. Now, sulfuric acid, as I told you, it's a king of chemical. So it is called as oil of vitriol. Its geometry is tetrahedral. It is oxidizing agent. It's a dehydrating agent. It's a strong acid. It's a strong acid. It undergoes complete dissociation. Therefore, it is called as a strong acid. Now we will learn the preparation of sulfuric acid. The sulfuric acid is prepared. One of the methods of preparing sulfuric acid was by a method called as lead chamber method. It's called as lead chamber method. We know that lead causes poisoning. Therefore, this method is not used now. So the method what we are using to prepare sulfuric acid is by a contact process. Contact process. 3 steps are there. Simple reactions, you need to pay attention. 3-4 steps we have. Contact process. The first step in the contact process is preparation of sulfur dioxide. Preparation of sulfur dioxide. Now, how can we prepare sulfur dioxide? We have learned in the previous topic, sulfur dioxide. Sulfur dioxide can be prepared by heating sulfur. Sulfur exists as S8. By burning sulfur, we can prepare sulfur dioxide. And also I taught you, in excess or in larger scale, sulfur dioxide can be prepared by roasting iron sulfide, iron pyrites. So iron sulfide, when you burn with oxygen, we get Fe2O3, iron oxide, and you get 8 sulfur dioxide gas. So sulfur dioxide in large quantity can be prepared by burning sulfur or by roasting iron pyrites, ferrous sulfide. Did you follow the first step of the reaction? Step 1. Step 2. The second step is this is important step. This is the principle of preparing sulfur dioxide. Oxidation of sulfur dioxide to sulfur trioxide. Oxidation of sulfur dioxide to sulfur trioxide. Sulfur dioxide is oxidized to sulfur trioxide. Sulfur trioxide. This is again 2 more balanced. 2 more sulfur trioxide. All are in gaseous state. Please write the physical states in the presence of vanadium pentoxide. The presence of vanadium pentoxide. Or we also can use platinum rhodium catalyst. Vanadium pentoxide can be used, or platinum rhodium catalyst can be used in order to prepare sulfur, in order to oxidize sulfur dioxide to sulfur trioxide. The step 3 is sulfur dioxide, when passed into water, it dissolves in water to form sulfuric acid. No doubt, traces of sulfuric acid will be formed. This is highly exothermic. Since it is highly exothermic, water will start vaporizing, and the sulfur dioxide will be absorbed, mixed with water, and it forms an acid fog. So dissolution of sulfur dioxide in water will not take place. Sulfur dioxide will not react with water to form sulfuric acid. Only little amount will be formed, and energy liberated is so very high, it forms acid fog. Dissolution of sulfur dioxide in water is restricted. Therefore, we are not dissolving sulfur dioxide in water. They can ask you why sulfur dioxide is not absorbed in water. You should remember and tell sulfur dioxide is not absorbed in water because sulfur dioxide forms sulfuric acid with liberation of large amount of heat. This large amount of heat which is liberated will not allow the sulfur dioxide to react with water to form sulfuric acid. Therefore, it forms an acid fog. You know what is a fog? Fog is nothing but oxygen with water will be called as a fog. A sulfur dioxide, which is acidic in nature, with water will be called as acid fog. So then what is the third step in the preparation of sulfuric acid by contact process? The third step in the preparation of sulfuric acid by contact process is absorption of sulfuric acid. Absorption of sulfur dioxide in concentrated sulfuric acid. Absorption of sulfur trioxide in concentrated sulfuric acid. So the sulfur trioxide which is formed in the second step is passed into concentrated sulfuric acid. Now this concentrated sulfuric acid absorbs the sulfur trioxide in the absorption tower. It is called as absorption tower to form fuming sulfuric acid, H2S2O7. This is called as fuming sulfuric acid. This fuming sulfuric acid is commonly called as oleum, O-L-E-U-M, oleum. This fuming sulfuric acid is called as oleum, H2S2O7. That's the molecular formula of oleum. Now, I didn't tell you the conditions here. Catalyst, I told you, the pressure is 2 atmospheric pressure and the temperature is 720 Kelvin. It's heated to around 500 degrees Celsius or 450 degrees Celsius, 720 Kelvin. This condition you should remember. So you need to remember the pressure as well as the temperature. Now the sulfur trioxide which is formed is absorbed in sulfuric acid concentrated. Step 4 is this fuming sulfuric acid which is formed, H2S2O7, sorry. This fuming sulfuric acid or oleum is diluted with calculated amount of water. Calculated amount of water. It's diluted with calculated amount of water. When you dilute it with calculated amount of water, this oleum H2S2O7 forms constant H2S2O4, 2 moles of H2S2, H2SO4, sorry, H2SO4 sulfuric acid. This is around 96 to 98% pure. It's around 96 to 98% pure. So these 3 or 4 steps you should remember in order to write the contact process. The first one, again, repetition. The first one is preparation of sulfur dioxide. How can sulfur dioxide gas be prepared? Sulfur dioxide is prepared by heating or burning sulfur oxygen or iron pyrites when roasted with oxygen, or roasted is heating with oxygen to form sulfur dioxide. Once the sulfur dioxide is formed, the second step is the sulfur dioxide is oxidized to sulfur trioxide. So this is the principle of contact process. If they ask you, write the principle of contact process for 3 marks, you should remember sulfur dioxide oxidation to sulfur trioxide is the principle. So sulfur dioxide oxidizes to sulfur trioxide in the presence of vanadium pentoxide as a catalyst or platinum rhodium as a catalyst at 2 atmospheric pressure and 720 Kelvin to form sulfur trioxide. Third step is sulfur trioxide is absorbed in concentrated sulfuric acid to form fuming sulfuric acid called as oleum. And this oleum is diluted with calculated amount of water to give concentrated sulfuric acid. Okay, is around 96 to 98% pure. Now, what are the properties of sulfuric acid? The properties of sulfuric acid. The physical properties of sulfuric acid. Pure sulfuric acid is highly viscous. It's highly viscous. Highly viscous. It's a syrup type liquid, and it's highly corrosive in nature. It's highly corrosive in nature. It produces burns on the skin. If it falls on the skin, it forms burns. It has strong affinity towards water and soluble in water, producing large amount of heat. It is soluble in water, producing large amount of heat. These are the physical properties of sulfuric acid. And a few more properties. As we discussed, sulfuric acid is a dibasic acid because it has 2 replaceable hydrogen. It's a dibasic acid or diprotic acid. It's a strong dehydrating agent, I told you, and it's also a strong oxidizing agent. We have learned chemical properties we are supposed to learn. Now, in case of chemical properties, firstly, we should understand the acidic nature of sulfuric acid. How do you prove that sulfuric H2SO4 is acidic in nature? Now, sulfuric acid, when added to water, sulfuric acid will donate H+ ion to water to form H3O+ and HSO4-. proton donors are called as acid, according to Bronsted-Lowry theory. So any chemical component which donates a proton will be called as acid. Since sulfuric acid donates proton to water, sulfuric acid is acidic in nature. Again, we know that NaOH is a very well-known base. When sulfuric acid is allowed to, H2SO4 is allowed to react with NaOH, we get sodium bisulfite. Finally, we get sodium sulfite. This sodium bisulfite and sodium sulfate is salt. They are salt. This is acidic salt and it's a normal salt. If NaOH is basic and salt is formed, that means the nature of H2SO4 should be acidic in nature. So acidic in nature. So these two reactions can prove that H2SO4 is acidic in nature. Now, three important questions we are going to learn. Three important questions. The first one is dehydration. Dehydration. Dehydration is removal of water. The removal of water is called as dehydration. Now, sulfuric acid is a very good dehydrating agent. Now, when we say sulfuric acid is a very good dehydrating agent, the first example we will take HCOOH, formic acid. This is formic acid. This formic acid, when allowed to react with concentrated sulfuric acid. Now, sulfuric acid being a very good dehydrating agent, what happens is it removes water. When it removes water, what is the product left out? The product left out is carbon monoxide. So formic acid, when treated with concentrated sulfuric acid, dehydration takes place, giving carbon monoxide. Likewise, if you take oxalic acid, this is oxalic acid. These are weak acid. Formic acid, oxalic acid is weak. Now, when this oxalic acid is treated with sulfuric acid, dehydration takes place. Water gets removed. Likewise, the bond between carbon to carbon breaks. So we get carbon dioxide gas and carbon monoxide gas, remember. So formic acid will give you a carbon monoxide. Oxalic acid on dehydration gives carbon dioxide and carbon monoxide. Likewise, if you take sugar, C12H22O11, this is sucrose. Sucrose is the sugar what we eat. This sucrose sugar, when it is treated with concentrated sulfuric acid, if you take sugar in a test tube, and to that if you add concentrated sulfuric acid, what happens is the sulfuric acid, being a dehydrating agent, removes water. When it removes water, left out is only carbon. So this carbon is black in color. So it's called as sugar charcoal. Sugar charcoal. Similarly, the same thing happens with glucose also. Glucose is C6H12O6. So when glucose is treated with concentrated sulfuric acid, you get carbon and you get 6 moles of water. So carbon black, you get sugar charcoal, or carbon black it is called as. So these are, this is the property of dehydration. So two property we learned, acidic nature we learned. We also learned with the property called as dehydration. The next property of sulfuric acid is oxidation property. Oxidation. Sulfuric acid, as I told you, it's a strong oxidizing agent. Why it is a strong oxidizing agent, we'll learn now. Now, anything which gives nascent oxygen will be called as an oxidizing agent. Sulfuric acid, on heating, it will decompose to form water, giving you sulfur dioxide gas and also giving nascent oxygen. Since sulfuric acid gives nascent oxygen, sulfuric acid is called as a good oxidizing agent. Now you can observe here, Now, copper, the charge on copper is 0. Now, when copper is treated with as a charge plus from 0 to plus 2. Whenever there's an increase in copper is oxidized to copper sulfate. Now you can see a sulfur treated with sulfuric acid. Sulfur charge is 0. The sulfur, the charge being 0 when treated with sulfuric acid, we get sulfur dioxide. Here the charge on sulfur is +4. So sulfur is oxidized to sulfur dioxide by concentrated sulfuric acid because of the property sulfuric acid gives nascent oxygen. Likewise, carbon, when you treat with concentrated sulfuric acid, carbon is oxidized to carbon dioxide. Carbon charge is 0. Carbon dioxide here, the charge of carbon is +4. So increase in charge is called as oxidation. So sulfuric acid concentrated is a good oxidizing agent. These are the properties of sulfuric acid. Now, uses of sulfuric acid. Now, sulfuric acid is used in the manufacturing of fertilizers, like ammonium sulfate. And superphosphate of lime. These are fertilizers, superphosphate of lime. Manufacturing of sulfuric acid. Uses of sulfuric acid, manufacturing of fertilizers like ammonium sulfate and superphosphate of lime. It's used in the manufacturing of explosives. Manufacturing of explosives like gun cotton. Gun cotton is called as nitrocellulose. Cellulose is a polymer, carbohydrate. Treated with nitric acid and sulfuric acid gives nitrocellulose. Gun cotton, it's called as. Preparation of trinitrotoluene, TNT, what is used in the manufacturing of picric acid. What is the full form of picric acid, or the IUPAC name of picric acid? Is 2,4,6 trinitrophenol. So all these are explosives. Sulfuric acid is used in the preparation of explosives. Third, it is used in refining petrol. In the purification of petrol, sulfuric acid is used. Sulfuric acid is used in the manufacturing of nitric acid and other acids, HCl, etc. So this is with respect to group 16. Any clarification with this today, what we've done so far? So that we can go for group 17. Okay.
No,
Okay. I hope that you understand the preparation of sulfuric acid by contact process and also dehydrating property of sulfuric acid. So I taught you 3 dehydration properties. So you should remember the dehydrating properties of sulfuric acid as well. Now, come to the 17th group elements. The 17th group elements are called as halogens. 17th group elements are called as halogens. Now, in the 17th group, we have 5 elements: fluorine, chlorine, bromine, iodine, and astatine, ASTATINE, astatine. This astatine is a radioactive halogen. Astatine is radioactive halogen, and it's found in very trace quantity. So we don't talk about astatine in general. So fluorine, chlorine, bromine, and iodine are the elements present in group 17. They are called as halogens. Now, atomic number, electronic configuration, and the group number, they are all present in group number 17. And fluorine is present in the 2nd period. Chlorine is in the 3rd period, and it's given that. And also astatine is present in the 6th period in the periodic table. Now, this is with respect to the general introduction of the halogen. Now, atomics and ionic radii. physical properties we are learning. Now, atomic and ionic radii, everybody knows that in the periodic table, the 17th group element is the smallest because they are highly electronegative compared to any other elements, any other group. Atomic radius. Halogens have the smallest atomic radii in their respective period. In the second period, fluorine is the smallest. In the third period, chlorine will be the smallest. All right. But we should understand that's because of the maximum effective nuclear charge, electronegative concept I told you. But as we go down the group, fluorine, chlorine, bromine, and iodine, as we go down the group, atomic size increases. That is the general trend in the periodic table. Down the group, the atomic size increases, but halogens are the smallest in the respective period. Second, ionization and enthalpy. Ionization, see, halogens are highly electronegative. It will have a tendency to attract electron to attain stability, F minus, fluoride ion. It will not tend to lose an electron. So ionization energy or enthalpy is the energy required to remove an electron from the outermost orbit. But here, fluorine electron will not be removed easily. It accepts electron easily. Therefore, they have very high ionization energy. It is because of the small size. Next, electron gain enthalpy. Electron gain enthalpy is otherwise called as electron affinity. Now, in the general trend, halogens have maximum negative electron gain enthalpy because elements have only one electron less than stable noble gas configuration. Electron gain enthalpy becomes less negative down the group because atomic size increases down the group. So electron gain enthalpy becomes less negative down the group. Actually, it is not. It is explained in other ways that fluorine has lesser electron gain enthalpy than chlorine, because fluorine is very small, so repulsive force takes place. Therefore, fluorine has lesser enthalpy than chlorine. And actually speaking, the electron gain enthalpy in the halogen fluctuates. It does not follow the general trend. It fluctuates, right? So fluorine has higher electron gain enthalpy than chlorine. So these are the physical properties. Electronegativity, these elements have highly electronegative. And electronegativity decreases down the group. As we go down the group, effective nuclear charge also decreases. Therefore, electronegativity also decreases. Dissociation enthalpy. This you should remember for competitive exams. Bond dissociation enthalpy is not a general trend here. Bond dissociation enthalpy follows the trend. Chlorine is greater than bromine. Bromine is greater than fluorine. Fluorine is greater than iodine. This is because the size increases. As the size increases, bond length increases. Bond dissociation enthalpy has to decrease. But chlorine is more than fluorine. Chlorine is more than fluorine because there are large electronic repulsion of lone pair of electron in fluorine. So actually speaking, bond dissociation enthalpy of chlorine should be less than that of fluorine. But here you can see chlorine is greater than that of fluorine. Why? Because more in case of fluorine. Therefore, what happened? Bond dissociation enthalpy will be less in case of fluorine. So this is the trend. You should remember this trend, bond dissociation enthalpy in fluorine. It's confusing, so they can ask you this question. Now, color. All halogens are colored because of absorption of radiation in visible region, which results in excitation. Now, fluorine is pale yellow. You should remember, fluorine is pale yellow. Chlorine is greenish yellow. Bromine, you would have seen reddish brown. Bromine is reddish brown. and iodine is violet, dark violet. Iodine is dark violet. So this is with respect to color. Oxidizing power. All halogens are strong oxidizing agents. All halogens are strong oxidizing agents because they have a strong tendency to accept electron. So anything which undergoes reduction will be called as oxidizing agent. So if fluorine, the charge is 0, if it accepts an electron, you get fluorine minus. So decreasing charge is called as a reduction. So the thing which happens reduction is called as an oxidizing agent. So fluorine is a strong oxidizing agent in halogen. Fluorine is strong oxidizing agent than chlorine. Chlorine is strong oxidizing agent than bromine, and bromine is strong oxidizing agent than iodine. Reactivity with hydrogen. Acidic strength. Hydrogen fluoride. See, halogens will react with hydrogen and halogen. Halogen is represented as X, so it gives you 2HX. So if it's fluorine, you get HF, hydrobromic acid. Now, acidic strength. HF is less stronger than HCl. HCl is less stronger than HBr. HBr is less stronger than HI. So the strongest among this is HI. Stability of these acids. Stability of these acids. So HF is stable compared to HCl. It's in the reverse order. This is because decrease in bond dissociation enthalpy. So bond dissociation enthalpy will be more for HF because fluorine is small, H is small. As the size decreases, bond dissociation enthalpy decreases. Remember that. So the answer for answer stability is HF is greater than HCl. HCl is greater than HBr, and HBr is greater than HI. Similarly, the boiling point. HCl is less than HBr, HBr is less than HI, HI is less than HF. HF has strong intermolecular hydrogen bonding. As the size increases, van der Waals force increases, hence boiling point also increases. See, we know that fluorine, chlorine, bromine, and iodine. As we go down the group, the size increases, the mass also increases. As the mass increases, the molecular mass also, the boiling point also should increase. So now HCl, HBr, HI are the highest boiling point. But in case of HF, even though the molecular mass is less, it forms intermolecular hydrogen bonding. Since it forms intermolecular hydrogen bonding, the boiling point of hydrogen fluoride is high compared to all other elements. Ionic character, HF is more ionic compared to other halides. And dipole moment is given by, dipole moment is represented by letter mu. It's nothing but charge into distance. Charge into distance. Now, the dipole moment is greater for HF because charge in fluorine is much higher than chlorine and bromine and iodine. Therefore, dipole moment is greater for HF compared to HCl, compared to HBr, compared to HI. The electron negativity decreases down the group, reducing power. All this we have learned. We will not having any, maybe we'll learn some of the questions. Maybe Friday we'll finish off with this chapter. Interhalogen compounds also we have. Almost halogens we have finished. Now we have to learn with interhalogen compounds. Chemical properties we have to learn. And also we will learn interhalogen compounds in the next week. So next class, that is on next class, and then we'll continue with some of the questions. Ma'am, I'll stop the class, ma'am.
Okay, sir. Thank you, sir. Thank you, sir. Yes, sir.
Thank you, sir.
Hello, ma'am.
Sir, am I audible? Thank you, sir.
Yes, ma'am. Bye.